Hello everyone. In previous class, we discussed about what is oscillator and its classification and RC phase shift oscillator. In this lecture, we will study about what is LC oscillator, what is Hartley oscillator, and the reference of this presentation. So in this lecture, we cover all these topics one by one. So let's start. With topic 1, oscillator introduction. An oscillator generates output without any AC input signal. An electronic oscillator is a circuit which converts DC energy into AC at a very high frequency. An amplifier with a positive feedback can be understood as an oscillator. तो ऑसिलेटर क्या होता है, हमने पिछले वाली क्लास में भी ये देखा था। ऑसिलेटर जो होता है वो एम्पलीफायर की तरह ही काम करता है, बट इसमें हम इनपुट सिग्नल नहीं देना पड़ता। इसमें हमें केवल डीसी सप्लाई देनी होती है और हमें आउटपुट मिलता है। इलेक्ट्रॉनिक ऑसिलेटर जो होते हैं वो कन्वर्ट करता है डीसी को एसी में बहुत हाई फ्रीक्वेंसी में। सो दिस इज द डेफिनेशन ऑफ ऑसिलेटर। This is LC oscillator. Oscillators are electronic circuits that generate a continuous periodic waveform at a precise frequency. Oscillators convert DC input into AC output, which can have a wide range of different wave shape and frequencies that can be either completed in nature or simple sine wave depending upon the application. Oscillators are also used in many pieces of test equipment, producing either sinusoidal wave, square, sawtooth, triangular shaped waveform, or just a train of pulses of a variable and constant width. So, LC oscillators are commonly used in radio frequency circuit because of their good phase noise characteristics and their ease of implementation. तो LC oscillator का जो commonly use होता है वो radio frequency circuits में use करते हैं। An oscillator is basically an amplifier with positive feedback or regenerative feedback. And one of many problems in electronic circuit design is stopping amplifier from oscillating while trying to get oscillator to oscillate. Oscillators work because they overcome the loss of their feedback resonator circuit either in the form of a capacitor, inductor, or both in the same circuit by applying DC energy at the required frequency into this resonant circuit. In other words, an oscillator is an amplifier which uses positive feedback that generate an output frequency without the use of input signal. Thus, oscillators are self-sustaining circuit generating an periodic output waveform at a precise frequency, and for any electric or electronic circuits to operate as oscillator, it must have the following three characteristics. Number 1, some form of amplification. Number 2, positive feedback or a regeneration. And number 3, a frequency determined feedback network. An oscillator has a small signal feedback amplifier with an open loop gain equal to or slightly greater than 1 for oscillation to start, but to continue oscillation, the average loop gain must return to unity. In addition to these reactive components, an amplifying device such as an operational amplifier or bipolar transistor is required. Unlike an amplifier, there is no external AC input required to cause the oscillator to work, as the DC supply energy is converted by the oscillator into AC energy at the required frequency. Basic oscillator feedback circuit. So this is the diagram of basic oscillator feedback circuit. ऑसिलेटर सर्किट में जो फीडबैक रहेगा वो हमें पॉजिटिव होना चाहिए. Where beta is a feedback fraction or feedback gain. ऑसिलेटर गेन विदाउट फीडबैक. पहले हम ऑसिलेटर गेन देखते हैं विदाउट फीडबैक. जब उन्होंने फीडबैक नहीं दिया है तब गेन क्या है. सो वोल्टेज गेन AV, A is called the gain and V is called the voltage. So AV is called the open loop voltage gain is equal to output voltage by input voltage. So AV is equal to V out divided by Vn. Or we can say that V out is equal to AV into Vn. Oscillator gain with feedback AV in bracket Vn minus of beta V out is equal to V out, where beta is the feedback fraction. AV into Vn minus of AV into beta into V out is equal to V out, where A into beta the loop gain. So AV into Vn is equal to V out 1 plus A into beta. 1 plus A into beta is equal to the feedback factor. So finally V out by Vn is equal to GV is equal to A upon 1 plus A into beta, where GV is called the closed loop gain. Oscillators are circuits that generate a continuous voltage output waveform at a required frequency with the value of the inductors, capacitor or resistor forming a frequency selective LC resonant tank circuit and feedback network. This feedback network is an alternation network which has a gain of less than 1, means beta less than 1, and start oscillation when A into beta greater than 1, which return to the unity, means A into beta is equal to 1 once oscillation commences. The LC oscillator's frequency is controlled using a tune or resonant inductive or capacitive circuit, with the resulting output frequency being known as the oscillation frequency. By making the oscillator feedback a reactive network, the phase angle of the feedback will vary as the function of frequency, and this is called phase shift. ऑसिलेटर रेजोनेंस. तो रेजोनेंस क्या होता है, व्हाट इज रेजोनेंस, आप लोगों ने ऑलरेडी 12th क्लास में स्टडी किया होगा, फिर भी मैं बता देता हूं. रेजोनेंस जो होता है एक्चुअली इट्स अ फ्रीक्वेंसी मैचिंग फिनोमेना. मींस जब XL इज इक्वल टू XC हो जाता है तो उस कंडीशन में हम रेजोनेंस बोलते हैं और उस कंडीशन में हम एक रेजोनेंस फ्रीक्वेंसी निकालते हैं. XL जो होता है वो हमारा क्या होता है, इंडक्टिव रिएक्टेंस, L मतलब इंडक्टर, X मतलब रिएक्टेंस, और XC इज इक्वल टू कैपेसिटिव रिएक्टेंस. तो जब XL इज इक्वल टू XC हो जाता है तो उस कंडीशन में हम रेजोनेंस बोलते हैं इन इलेक्ट्रिकल सर्किट एज वेल एज द इलेक्ट्रॉनिक सर्किट. So when a constant voltage but of varying frequency is applied to a circuit consisting of an inductor, capacitor and resistor, the reactance of both the capacitor oblique resistor and the inductor oblique resistor circuit is to change both the amplitude and the phase of the output signal as compared to the input signal due to the reactance of the component used. At high frequencies, the reactance of a capacitor is very low, acting as a short circuit while the reactance of the inductor is high, acting as an open circuit. At low frequencies, the reverse is true. The reactance of the capacitor act as an open circuit and the reactance of the inductor act as a short circuit. Between these two extremes, the combination of the inductor and the capacitor produce a tuned or resonant circuit that has a resonance frequency Fr, in which the capacitive and inductive reactances are equal and cancel out each other, leaving only the resistance of the circuit to oppose the flow of current. This means that there is no phase shift as the current in phase with the voltage. तो रेजिस्टिव लोड जब हमारे पास रहता है उस कंडीशन में जो हमारा वोल्टेज रहता है वो करंट के साथ हमेशा सेम फेज में होता है. सो कंसीडर अ सर्किट बिलो. Basic LC oscillator tank circuit. So this is the basic LC oscillator tank circuit. इसमें हमने एक L और एक C को कनेक्ट किया हुआ है और एक वोल्टेज सोर्स लगा हुआ है. This is the two-way switch. So this is called the LC oscillator tank circuit. The circuit consists of an inductor coil L and a capacitor C. The capacitor stores energy in the form of an electrostatic field and which produce a potential across its plates, while the inductive coil stores its energy in the form of electromagnetic field. The capacitor is charged up to DC supply voltage and V by putting the switch is position A. While the capacitor is fully charged, the switch changes to the position B. The charged capacitor is now connected in parallel across the inductor coil. So the capacitor begins to discharge itself through the coil. The voltage across C starts falling as the current through the coil being to rise. नॉर्मली होगा क्या कि पहले हम इस स्विच को ए पे कनेक्ट करेंगे तो जो हमारा कैपेसिटर है वो फुल्ली चार्ज हो जाएगा. जब चार्ज हो जाएगा तो हम इस स्विच को बी पे मूव कर देंगे जिससे कि जो कैपेसिटर है वो इंडक्टर कॉइल के थ्रू डिस्चार्ज होना स्टार्ट होगा. This rising current set up an electromagnetic field around the coil which resists the flow of current. When the capacitor C is completely discharged, the energy that was originally stored in the capacitor C as an electrostatic field is now stored in the inductor coil L as an electromagnetic field around the coil windings. As there is now no external voltage in the circuit to maintain the current within the coil, it starts to fall as electromagnetic field being to collapse. A back EMF is induced in the coil according to Faraday law. So E is equal to minus of L di by dt, keeping the current flowing in the original direction. This current charge up capacitor C with the opposite polarity to its original charge. C continues to charge up until the current reduced to zero and the electromagnetic field of the coil has collapsed completely. The energy originally introduced into the circuit through the switch has been returned to the capacitor, which again has electrostatic voltage potential across it, although it is now to the opposite polarity. The capacitor now starts to discharge again back through the coil and the whole process is repeated. The polarity of the voltage change as the energy is passed back and forth between the capacitor and inductor, producing an AC type sinusoidal voltage and current waveform. This process then forms the basic of an LC oscillator tank circuit, and theoretically this cycling back and forth will continue indefinitely. However, things are not perfect, and every time energy is transferred from the capacitor C to the inductor L and back from L to C, some energy losses occurs which decay the oscillation to zero over time. This oscillatory action of passing energy back and forth between the capacitor C to the inductor L would continue indefinitely if it was not for energy loss within the circuit. Electrical energy is lost in the DC or real resistance of the inductor coil, in the dielectric of the capacitor, and the radiation from the circuit, so the oscillation steadily decrease until they die away completely and the process stops. Then, in a practical LC circuit, the amplitude of the oscillatory voltage decreases at each half cycle of the oscillation and will eventually die away to zero. The oscillations are then said to be damped, with the amount of damping being determined by the quality or Q factor of the circuit. Now next is the damped oscillation. So this is the diagram of damped oscillation. First one is small r, lightly damped, longer time, and second large r, heavily damped, shorter time. The frequency of the oscillatory voltage depend upon the value of inductor and capacitor in the LC tank circuit. We now know that for resonance to occur in the tank circuit, there must be the frequency point where the value of XC, the capacitive reactance, is the same as the value of XL, the inductive reactance. Means XL is equal to XC, and which will therefore cancel out each other, out leaving only the DC resistance in the circuit to oppose the flow of current. If we now place the curve of inductive reactance of the inductor on top of the curve for the capacitive reactance of the capacitor, so that both curves are the same frequency axis, the point of intersection will gives us the resonance frequency point Fr or omega r as so below. So this is the diagram for resonance frequency, and this is the point where XL is equal to XC. इस वाले पॉइंट पे ये जो पॉइंट दिख रहा है, इस वाले पॉइंट पे हमारा XL is equal to XC हो जाएगा, तो इसी वाले पॉइंट पे हमें रेजोनेंस फ्रीक्वेंसी Fr जो है वो मिलेगी, where Fr is in Hertz, L in Henry, and C in Farad. Then the frequency at which this will happen is given as XL is equal to 2 pi FL and XC is equal to 1 upon 2 pi F into C. At resonance XL is equal to XC, so 2 pi FL is equal to 1 upon 2 pi FC, दोनों की वैल्यू पुट कर दी, so 2 pi F square L is equal to 1 upon 2 pi C, then F square is equal to 1 upon 2 pi square into LC. So finally the frequency, resonance frequency F is equal to 1 upon under root 2 pi square into LC. So the final frequency F is equal to 1 upon 2 pi under root of LC. Then we simplifying the above equation, we get the final equation of the resonance frequency Fr in the tuned LC circuit as resonance frequency of LC oscillator Fr is equal to 1 upon 2 pi under root of LC, where L is the inductance in Henry, C is the capacitance in farads, and Fr is the output frequency in hertz. This equation shows that if either L or CR decreases, the frequency increase. This output frequency is commonly given the abbreviation of Fr to identify it as the resonance frequency. Small r matlab resonance or F means frequency. To keep the oscillation going in an LC tank circuit, we have to replace all the energy lost in each oscillation and also maintain the amplitude of these oscillations at a constant level. The amount of energy replaced must therefore be equal to the energy lost during each cycle. If the energy replaced is too large, the amplitude would increase until clipping of the supply rails occurs. Alternatively, if the amount of the energy replaced is too small, the amplitude would eventually decrease to zero over the time and the oscillation would stop. The simplest way to replacing this lost energy is to take part of the output for the LC tank circuit, amplify it, and then feed it back into the LC circuit again. This process can be achieved using a voltage amplifier, using a op-amps means operational amplifier, FET or bipolar junction transistor as its active device. However, if the loop gain of the feedback amplifier is too small, the desired oscillation decay to zero, and if it is too large, the waveform becomes distorted. To produce a constant oscillation, the level of the energy feedback to the LC network must be accurately controlled. Then there must be some form of the automatic amplitude or gain control when the amplitude tries to vary from a reference voltage either up or down. To maintain a stable oscillation, the overall gain of the circuit must be equal to 1 or unity. Any less and the oscillations will not start or die away to zero. Any more, the oscillation will occur but the amplitude will become clipped by the supply rails, causing distortion. Consider the circuit below. So next is a basic transistor LC oscillator circuit. So this is the diagram of basic LC oscillator circuit by using the transistor. A bipolar transistor is used as LC oscillator amplifier with the tuned LC tank circuit act as the collector load. Another coil L2 is connected between the base and the emitter of the transistor, whose electromagnetic field is mutually coupled with that of the coil L. Mutual inductance exists between the two circuits and the changing current flow in one coil circuit induced by electromagnetic induction. A potential voltage in the other so as the oscillation occur in the tuned circuit. Electromagnetic energy is transferred from coil L to coil L2 and a voltage of the same frequency as that in the tuned circuit is applied between the base and emitter of the transistor. In this way, the necessary automatic feedback voltage is applied to the amplifying transistor. The amount of feedback can be increased or decreased by altering the coupling between the two coils L and L2. When the circuit is oscillating, its impedance is resistive and the collector and the base voltage are 180 degree out of phase. In order to maintain oscillation, the voltage applied to the tuned circuit must be in phase with the oscillation occurring in the tuned circuit. Therefore, we must introduce an additional 180 degree phase shift into the feedback path between the collector and the base. This is achieved by winding the coil of L2 in the correct direction relative to coil L, giving us the correct amplitude and phase relationship for the oscillator circuit, or by connecting a phase shift network between the output and input of the amplifier. The LC oscillator is therefore a sinusoidal oscillator or harmonic oscillator, as it is more commonly called. LC oscillator can generate high frequency sine wave for use in radio frequency type application, with the transistor amplifier being of a BJT or FET. Harmonic oscillators come in many different forms because there are many different ways to construct an LC filter network and amplifier, with the most common being the Hartley LC oscillator, Colpitt's LC oscillator, Armstrong oscillators, and Clap oscillator, to the name of few. Next is the LC oscillator example 1. An inductance of 200 millihenry and a capacitor of 10 picofarad are connected together in parallel to create an LC oscillator tank circuit. Calculate the frequency of oscillation. अब इस न्यूमेरिकल के थ्रू हम देखेंगे कि हम frequency of oscillation कैसे निकाल सकते हैं. इसमें हमारे लिए इंडक्टेंस की वैल्यू गिवन है एंड कैपेसिटेंस की वैल्यू भी गिवन है. चलिए देखते हैं. So the frequency, we know that frequency or resonance frequency is equal to 1 upon 2 pi under root LC. So put the value of L and C. So 1 upon 2 pi under root 200 millihenry into 10 picofarad. So we get 1012.5 kilohertz. Then we can see from the above example that by decreasing the value of either the capacitance C or the inductance L will have the effect of increasing the frequency of oscillation of LC tank circuit. इसका मतलब अगर हम L या C की वैल्यू को चेंज करते हैं या डिक्रीज करते हैं तो जो हमारा फ्रीक्वेंसी है, रेजोनेंस फ्रीक्वेंसी, वो इंक्रीज होती है. नेक्स्ट इज LC ऑसिलेटर समरी. चलिए देखिए हमने LC ऑसिलेटर्स में क्या क्या पढ़ लिया है. The basic condition required for an LC oscillator's resonant tank circuit are given as follows. Number 1. For oscillation to exist, an oscillator circuit must contain a reactive component, either an inductor or a capacitor, as well as a DC power source. मतलब अगर हमें LC ऑसिलेटर बनाना है तो उसके लिए मस्ट कंडीशन है हमारे पास रिएक्टिव कंपोनेंट्स होना चाहिए, या तो इंडक्टर या कैपेसिटर और डीसी सप्लाई हमारे पास होनी चाहिए. इन अ सिंपल इंडक्टर कैपेसिटर LC सर्किट ऑसिलेशन बिकम डैम्प्ड ओवर टाइम ड्यू टू द कंपोनेंट्स एंड द सर्किट लॉस. Number next, voltage amplification is required to overcome these circuit losses and provide positive gain. तो वोल्टेज एम्पलीफिकेशन की ज़रूरत हमें होती है मिनिमाइज करने के लिए जो हमारे लॉसेस हो रहे हैं उसको, और पॉजिटिव गेन प्रोवाइड करने के लिए. द ओवरऑल गेन ऑफ एम्पलीफायर मस्ट बी ग्रेटर देन 1 और यूनिटी. तो जो ओवरऑल गेन है हमारे LC ऑसिलेटर का वो 1 से ज़्यादा होना चाहिए. Oscillations can be maintained by feeding back some of the output voltage to the tuned circuit that is of the correct amplitude and in phase, means 0 degree. Oscillation can only occur when the feedback is positive. तो LC ऑसिलेटर में हमारे ऑसिलेशन कब होंगे ऑकर्स? जब हमारा फीडबैक जो है वो पॉजिटिव होगा, नेगेटिव होगा तो नहीं होंगे. The overall phase shift of the circuit must be 0 or 360 degree so that the output signal from the feedback network will be in phase with the input signal. So this is all about LC oscillators. LC ऑसिलेटर्स क्या होते हैं, उसका सर्किट डायग्राम और उसकी रेजोनेंस फ्रीक्वेंसी और LC टैंक सर्किट हम कैसे बना सकते हैं, ये सब हमने इस लेक्चर में देखा. इन द नेक्स्ट लेक्चर अबाउट ऑसिलेटर वी विल एग्जामिन द ऑपरेशन ऑफ one of the most common LC oscillator circuit that used two inductance coils to form a center-taped inductance within its resonant tank circuit. This type of LC oscillator circuit is commonly known as हार्टले oscillator. तो नेक्स्ट वाले लेक्चर में अब हम स्टडी करेंगे हार्टले ऑसिलेटर्स के बारे में, उसका सर्किट डायग्राम, उसका रेजोनेंस फ्रीक्वेंसी और कैसे हम हार्टले ऑसिलेटर्स को डिजाइन कर सकते हैं, ये हम देखेंगे नेक्स्ट लेक्चर में. सो द नेक्स्ट इज हार्टले ऑसिलेटर्स. इसको हम नेक्स्ट लेक्चर में कवर करेंगे. After this, the references of this presentation. So these are the references. And thank you for watching this video.